Yeah. Okay. Well, good afternoon, everyone. So let's begin. Right. So we'll quickly do a recap, and I also want to correct a few things from the last lecture, just related to terminology. Yeah. So, anyways, let's just recap what the perfect matching polytope is. Is the set of all convex combinations of perfect matchings of the graph, right? So for each perfect matching, you may view it as a vector. This is called the incidence vector, and then you just multiply it by coefficient alpha I. All the alpha i's are non-negative, and their sum is equal to 1, which is the definition of convex combination, right? So that's what the perfect matching polytope is. One quick example that we also saw last time. Of course, every perfect matching, its incidence vector is in the polytope, but you can also have other vectors, like I put a 0.5, I put a half on all of these 4 edges of the 4 cycle, and I put a 1 over here. That is half times one perfect matching plus half times the other perfect matching, another perfect matching, right? So therefore, this is also in the polytope. G is your graph, triangular prism, right? Okay. All right. On the other hand, this vector let's put a half on all the 6 edges of the 3 cycles and 0 everywhere else. This, it does satisfy 2 of the conditions that we discussed, the 2 necessary conditions to belong to the polytope. Each coordinate has to be greater than or equal to 0. These are called the non-negativity conditions, as they should be. The sum at each vertex is equal to 1. That is true. Half plus 0 is 1. These are called the degree constraints. And it does satisfy these 2, but it is not in the perfect matching polytope, because you can look at this odd cut, and the sum on this cut is 0, but every perfect matching has to meet every odd cut at least once. Therefore, it cannot be 0 in a convex combination, right? So the reason it is not in the polytope is because it violates another condition, which is probably not as obvious as the first 2 conditions, but is not too unobvious either, right? These are called the odd set constraints. You can also call them odd cut constraints, but then you have to be careful, because now by odd cut, we mean a cut whose at least one of the 2 shores is odd, because it is a statement about all graphs. So I could have an odd number of vertices, and there also it is a problem, right? Even if you have an odd number of vertices, it does violate an odd cut constraint, right? The cut corresponding to all the 3 vertices. That is an odd cut. And we may also call them Edmonds constraints. Since Edmonds proved that if you include the odd set constraints, then actually you have the entire perfect matching polytope completely characterized. In other words, a vector in Re belongs to the polytope if and only if it satisfies this set of constraints. So that is Edmonds' result. Let G be any graph. We don't need any hypothesis here. A vector x in Re belongs to the polytope, the perfect matching polytope corresponding to this graph, if and only if it satisfies non-negativity, degree, and the odd set constraints. And this is what we will prove today. The remark I want to make about the terminology is I also call this regularity condition. I said that we will say that the vector is one regular. Turns out in Lucchesi-Murty, they actually use one regular and regular for a slightly more general thing. They want for every vertex they want the sum to be equal to 1, but they actually want it for every tight cut. So when it holds for every tight cut in the context of matching covered graphs, they call it a one regular vector or just a regular vector if the sum is the same across all tight cuts, which includes the trivial cuts, but it also includes the non-trivial cuts. So I'm not going to use that terminology. I'll just call these the degree constraints. Okay, I shall not call them one regularity or regularity because that's reserved for something else in the book. Yeah. Okay, questions, concerns? Yes, go ahead.
1965, so is it related to
yes.
the algorithm?
Yes, absolutely. So in fact, a good point. So one of the major open problems in graph theory, combinatorial optimization, algorithms, etc. was basically deciding whether a graph has a perfect matching or not. But in fact, people were interested in more general versions. Finding a minimum cost perfect matching, which is something Meghna might cover in her course, for example, right? Or I will actually cover it in LPCO. Most likely next semester I'll be offering that, right? So that was a major open problem back in the day. Tutte had proved Tutte's perfect matching theorem in 1947. So already at that point, for perfect matchings or even for maximum matchings, Tutte-Welch formula came around the same time, not too far away, I guess. People knew NP and co-NP characterizations, but a P characterization wasn't known. In other words, a polynomial time algorithm for these problems wasn't known. And that was a major problem settled by Edmonds. Edmonds actually just killed a bunch of problems in one shot. Right? So you can compute a minimum cost perfect matching, you can find a maximum weight, a maximum matching of maximum weight, minimum weight doesn't really matter. And in the same series of works or work, I don't know, Edmonds also got this. In fact, the proof that Edmonds got of this is actually algorithmic. At the end of the algorithm, you see a certificate that actually proves this. I think I discussed this more in the LPCO course. But what we will see is a non-algorithmic proof. That turns out to be really, really short depending on which sources you refer to. Right? So yeah, so in fact it is related to all those discoveries and breakthroughs. So this 1965 was basically a very important year for, especially for combinatorial optimization. It is generally regarded to be the point where combinatorial optimization was born as a field. That's how important this was. Yeah. Okay, good. Any other questions, concerns? I was going to say constraints. No constraints. Okay. Right. So let's prove this. One direction is easy, right? You all agree that we can already see that if a vector belongs to the perfect matching polytope, then it must satisfy non-negativity, degree, and the odd set constraints. So that is the easy direction. We just need to prove the other direction. So this is easy. Okay. So what we'll do is we will define two polytopes. One is the perfect matching polytope, and another is the polytope defined by this set of constraints. This set of constraints will also give you a polytope, right? The question is, are the two polytopes equal? Yeah. So we won't give it a name because we are going to prove that they are equal. We'll just call it P of G. So any P of G is the set of all those vectors that satisfy these constraints. And what Edmonds theorem says is that poly of G is equal to P of G. This is equivalent to saying that the perfect matching polytope is equal to P of G. Yeah, it's kind of not fun to say P of G. I'll just call it Edmonds Polytope. Is that okay? I think I should give it a name because I have to speak it. I don't want to speak P of G. Edmonds Polytope. It's worth noting that the S is part of the name. So if you want to say Edmonds, you have to put the apostrophe afterwards. Right? Okay. And what does this tell you? What does this tell you? The forward implication is saying that the perfect matching polytope is contained in Edmonds Polytope. That is easy. Right. Proof. Clearly, the easy direction. The perfect matching polytope is contained in Edmonds Polytope. It remains to show the other containment. Right? Any vector that satisfies all of these inequalities, we need to prove that it is indeed in the perfect matching polytope. Questions, concerns? But the point is that they're both polytopes. That's kind of nice. Let's make a drawing where a polytope is not contained in the other polytope, just for the sake of visualization. So basically what we want to do, if you think about it in 2D, that's as good as my drawing gets here. If this is my perfect matching polytope, what we are trying to show is something like this does not happen. Right? We are trying to show that this set, whatever you see here, is empty. In other words, yeah, this is not a Venn diagram. This is, and it can be viewed as a Venn diagram, but I meant to view it as a polytope diagram in 2D. Right? So this is, you want to get a contradiction to this. Let me ask you a question. If you want to show that this is a subset of this, does it suffice to show that the extreme points of this are contained in this set? If we show that the extreme points, remember what the extreme points are. It is those points that cannot be written as convex combinations of other points. But all other points in the polytope can be written as convex combination of the extreme points. Right? For a polytope, all points can be written as convex combinations of extreme points, including the extreme points, the trivial convex combination of themselves with others. Right? So if we argue that the extreme points of this fellow are contained in this, then we are done. In other words, if this containment is strict, then there is an extreme point of this fellow that is not here. If this is a strict containment, then there has to be an extreme point of this fellow that is not contained here. Because if all the extreme points are here, then all the points are here. Yeah, let me write it down. It suffices to argue that each extreme point of Edmonds Polytope lies in the perfect matching polytope. If you want to show that one cube lies in another cube in 3D, it suffices to check that the corners of the first cube are inside the second cube. If all the corners are in the second cube, then well, the whole cube is inside. Right? At least in 3D, I hope you all can see this. Right? If it goes out, there's some corner that is also jutting out. Right? Yeah. Okay? Good. So let's do this. Let's prove that the extreme points indeed lie in the extreme points of Edmonds Polytope lie in the perfect matching polytope. Yeah. To this end, let X be an extreme point of Edmonds Polytope. Yeah. I forgot to mention the proof is by induction. You may say, how, what are you going to induct on? You're going to induct on the number of vertices. How? We'll see. The proof is by induction. Okay, so by induction on order. So if we get a smaller graph, then for the smaller graph we can assume that the two polytopes are equal. In particular, Edmonds Polytope is indeed contained in the perfect matching polytope. Yep. Okay. Right, but when we get a smaller graph, we should also get a corresponding vector, right? Otherwise, how will we use the induction hypothesis? Right? We also need to a natural way to get a vector for the smaller graph. Then we have to argue that that vector satisfies Edmonds constraints for the smaller graph, and therefore it belongs to the perfect matching polytope of the smaller graph. Right? Okay. Let's do an example. So I want to illustrate this entire proof through the use of an example. I'll take the example directly from Lucchesi-Murty. Also happens to be a very beautiful graph. Okay, let's see. I'm going to need space in life. Let me make more space. Okay. Alright. That's going to be our graph. 1/6, 1/3, half. That means this has to be half. This has to be 1/6, and this has to be 1/3. And here we are going to consider 1/6 and half, 1/6 and 1/3 here, and half and therefore 1/3 here, but we will consider 1/3, 1/3 here. Okay. Check that this satisfies Edmonds constraints. Well, you don't need to check all the constraints right now. You can check non-negative degree and assume that it satisfies Edmonds constraints. Okay? So check that it's non-negative. I did not put any negative numbers. And if you look at any vertex, you have two possibilities in this example. Either it is half plus 1/3 plus 1/6, which adds up to 6/6. And or it is on this vertex, it is 1/3, 1/3, 1/3. Are there any other possibilities? Yeah, there are two vertices where it is 1/3, 1/3, 1/3, this one and this one. Yeah, that adds up to 1 again. Yeah? Yes, go ahead.
P of T is the set of points or vectors satisfying these three conditions.
That's right.
So is it a polytope? Because,
Yes.
string points,
Because it is a intersection of a finite number of half spaces, right? It follows that it is therefore a convex polytope. Yes. Right? Yeah. So in fact, both of these are polytopes, and we only need to argue that the extreme points of this fellow lie in this polytope. If the extreme points lie here, then the whole polytope has to lie in there. Yeah. Okay. Good. Okay. So now in the proof, consider an extreme point of Edmonds polytope. The vector that is shown here need not be an extreme point. It is only for illustrating parts of the proof. Okay? But it is in the polytope that we will actually see. Okay. So to proceed by induction, we will suppose, of course if it doesn't hold then we have to argue for the other case. But suppose there is a cut. Suppose there is an odd cut where the sum is equal to 1. Then we will actually obtain smaller graphs and finish the proof by induction. If there is no such cut, then we will have to deal with that case. Okay, so there will be two cases, and I also want to make a couple of more remarks. So the two cases are case 1. Let me make one more point actually before I make case 1. I want to make one more point, which is that if Edmonds polytope is empty, then there is nothing to prove, because the empty set is a subset of anything you like. Yeah. So we can assume that Edmonds polytope is non-empty. This actually implies that the graph has a perfect matching, DIY. Okay. So one small remark that I wanted to make. This is what we want to show. If Edmonds polytope is empty, then we are done. Now suppose that Edmonds polytope is not empty. Argue that the graph is a perfect matching. Well, the only way to argue is using Tutte's theorem. So DIY use Tutte's theorem to argue that G is actually matchable. which in particular implies that the number of vertices is even. Okay. Case 1. There is a non-trivial odd cut where the sum is equal to 1. There exists a non-trivial, now I mean the usual way because now I have an even number of vertices. There exists a non-trivial odd cut C such that x of C, the sum of all the components corresponding to C, is equal to 1. That happens here. Here is a cut C, and the sum across this cut is half plus 1/6 plus 1/3, which equals 1. Yeah? Okay. In this case, we will obtain two smaller graphs. You can imagine how we will obtain two smaller graphs. That should be fairly straightforward at this point. And we will argue that the corresponding vectors again satisfy Edmonds constraints for the smaller graphs. Therefore, in the smaller graph, they belong to the perfect matching polytope. Okay. And then we will use that fact to show that in the bigger graph also, they belong to the perfect matching polytope. The original vector belongs to the perfect matching polytope. Then we'll be done, right? Because we wanted to show that x belongs to the polytope. Right? Okay, so this is going to be one case. And the other case is going to be not case 1. For every non-trivial odd cut, the sum is not equal to 1. Therefore, it has to be greater than, no, this is not perfect matching.
Oh.
That it has to be greater than 1. Because Edmonds constraints say that it has to be at least 1.
Oh, so not every. Oh, we still don't know every
Right.
extreme point is a perfect.
No, we don't know that. Yeah. Yeah. Right. So this is case 1. Let me also just write case 2. Well, the summary is, it is not case 1. In other words, for every non-trivial odd cut, C, x of C is strictly greater than 1. Yeah? These are the two cases we will deal with. Okay. Questions, concerns? All good? So this is where I refer to multiple sources. So case 2, I want to show you two proofs. One from Lucchesi-Murty, which uses graph theory only, and one from Schreiber that just destroys it by using knowledge from linear algebra, including some polytopes knowledge, some of which I covered in LPCO, but I won't cover it here. I will just tell you that the following is true, and we will just use that and finish it off. But first, I'll show you the graph theoretical proof for case 2 when we go to case 2. Case 1, essentially they have the same approach, whether you look at Schreiber or Lucchesi-Murty, and they actually give credit. Schreiber actually mentions who are the different authors who basically found the same proof, modulo further shortening it, etc., etc. There are a bunch of authors. One of them I think is Seymour, but there are a few others. I don't remember all the names. Right. Okay. For case 1, I want to use this example. Yeah. So let's get two smaller graphs. So the idea in case 1 is to actually apply induction. In case 1, right? So we have a non-trivial odd cut where the sum is equal to 1. We want to get two smaller graphs. Yeah, everybody sees how to get the two smaller graphs. There is no debate on this, right? The graph is not matching covered, but so what? You can shrink a set of vertices and get a graph. That's not a problem. Okay, so we'll shrink the two shores of this cut into single vertices. We'll get two smaller graphs, and the vectors are also clear, right? Take the restriction of the original vector to the smaller graphs. Let's do it here in this example. So if I shrink the right hand side, so I'll put 1/6 here, 1/3 here, and half here. And now I shrink the right hand side to a single vertex. And I take the restriction. So this will be half, this will be 1/6, and this will be 1/3. And the sum at the vertex is equal to 1, well, naturally, because the cut sum was 1, right? Okay, so this is 1. This is my graph G1, and this is my vertex vector x1. Is that okay? G1 comma x1. Now let's do G2 x2 for shrinking this into single vertex. Okay. Okay. 1/6, 1/3, half, 1/3, 1/3, 1/3, and half, 1/6, 1/3. Yeah, these are our G1 and G2, and this is the vector x2. We have two smaller graphs. We have vectors for those smaller graphs. We want to apply induction, so therefore we should show that x1 belongs to the Edmonds Polytope with respect to G1, x2 belongs to the Edmonds Polytope with respect to G2. If we show that, then by induction they also belong to the perfect matching polytope. Therefore there are convex combinations of perfect matchings in those graphs, and then we have to show that they are actually convex combinations. The original x is a convex combination of appropriate perfect matchings in the original graph. Right? Okay, so DIY, a bunch of DIYs. G1 x1, well, let me just say x1 belongs to Edmonds Polytope for the graph G1, x2 belongs to Edmonds Polytope for the graph G2. If you solve this DIY, then it follows by the induction hypothesis that x1 belongs to the perfect matching polytope of G1 and x2 belongs to the perfect matching polytope of G2. Because it is a non-trivial cut, they have fewer vertices, that is clear, right? Therefore, you can write x1 as a convex combination of perfect matchings of G1, and you can write x2 as a convex combination of perfect matchings of G2. Okay, is that fine? Then we'll have to argue. Then the next DIY will be to use the convex combinations here to show that the original x belongs to the perfect matching polytope of G. Right? If we do that, we are done. We wanted to show that extreme point lies in this. So therefore, done. Yeah? Okay, so these are the two DIYs. See if you can settle the first DIY and I will come around. Make sure you go through all the constraints, right? Don't be lazy. first one is fine.
There is constraint that is not satisfied, then you take the original and the same constraint will be satisfied.
Oh. Okay, good. Now try the second one. For the second one, try to see if you can figure it out for rational numbers. When are you about arbitrary numbers? Anyone else? Good, anyone else? Okay, anyone else? For those of you who are done with DIY 1, if you are struggling with DIY 2, try not to think about all real numbers. Try to deal with rational numbers. And just see if you can figure it out for rational numbers. Yeah. If I confuse you further, sorry about that. DIY 1 or 2? 2. Okay, what about 1? 1 is done? want to discuss DIY1?
Think about any output in G1. Is it related to output in G? In G, it satisfies the suffices. If you take any output in G1, it's the output in G. That is satisfied. So that's how you have to do this instruction.
Okay, so let's just quickly discuss DIY1. Right, so I won't write down things. So let's just see why this is true. Well, non-negative is clear. We just took the restriction to the graph, so definitely we did not introduce any negative numbers. Degree constraints. Well, all the vertices of G1 except for the contraction vertex are vertices of G, and the edge sets are the same. So the sum was equal to 1 earlier, the sum is still equal to 1. For the contraction vertex, well, it is equal to 1 because of the case we are in. The case says x of c is equal to 1. That is the sum set of edges incident at the contraction vertex. So therefore, it is satisfying all the degree constraints. And for Edmonds constraints, observe that every odd cut of G1 is an odd cut in G. Right? And that is where we use this fact. We concluded the number of vertices even, we shrunk an even odd number of vertices in a single vertex. In fact, our cases, the way they are written, they are already relying on the fact that there is an even number of vertices. I am using the standard definition of odd cut, which applies to even number of vertices. Right? So every odd cut in G1 is an odd cut in G. There the sum was greater than equal to 1. So the sum is also greater than equal to 1 here because it's just a restriction. Right? So therefore, we are done with this and this. Therefore, by the induction hypothesis, x1 is in the perfect matching polytope of G1, x2 is in the perfect matching polytope of G2. Okay. Now we need to show that x is in the perfect matching polytope of G. It is much easier if you don't care about real numbers. So let's just try to do that. Let's just try to deal with fractions. Okay. So let's try to work out these two examples, right? I will probably get rid of the constraints because I'm sure you all remember the constraints by now. Let's write down these two vectors as convex combinations of perfect matchings of the corresponding graphs, right? One of them is very easy. Maybe I'll use colors now. Okay. All right. So this vector is simply 1/6 times m1 plus half times m2 plus 1/3 times m3. Yeah. M1, maybe I'll call M2 the blue one, okay. Maybe I'll make blue M2 and I'll make pink M3, fine. Alright. So it is 1/6 times M1 plus 1/3 times M2 plus half times M3. Yeah, that is very clear. Okay, let's deal with this example now. Can you all try to figure out how to write this vector as a convex combination of perfect matchings of this graph? If you figure it out, come and make a neat drawing here. me, and in general, if you want to discuss DIY2, or if you have already figured out how to generalize from rationals to reals, let me know and I'll come and talk to you. Yeah? Okay? Can you just come up with a formula? Can you just come up with, so given your alphas for the x1 and given your alphas for x2, the convex combination coefficients, can you basically tell me what are your alphas for the original graph? See if you can figure that out. I may not even discuss that, but I'm going to restrict to rationals, but I will explain why restricting to rationals is actually enough sense. Yeah, basically you can just come up with a formula. Yeah. Sorry? Labelings are correct. Yes, this is that. Yeah. Okay, anybody else? And if you have figured out this example, please let me know.
Sorry, V1 and then the perfect matching of G2. Take the product and put it in the numerator. You take the number of perfect matching of G2 and put it in the numerator. Number of the alphas of perfect matching of G1. So you get fraction times alpha. You can do this kind of. Just make multiple copies with smaller coefficients and so that you can match them. That
sounds more complex than it is.
Oh.
I mean, I think you have the idea, but see if you can make it more complicated. I'm not convinced. It sounds a bit vague to me.
Okay.
Showing multiples.
This for each edge. So mi union edges defined. These mutual add up to the same time.
Let's work out on this example.
I have to normalize this. I have to divide it by the total weight of the edge.
So this example, anybody found the perfect matchings for which this vector is a convex combination? I mean, one thing that is sort of clear, well, at least something that is worth trying, is taking 1/6 time a certain perfect. So 1/6 is the smallest number in all the numbers I've used. So I can take 1/6 times this perfect matching. That takes care of, now you can try subtracting 1/6 from those numbers and try to proceed. So I'll just write down 1/6 times this. and this is going to correspond to my M1 in some sense because the yellow edge, so I'll call it N1. So 1/6 times N1 now see if you can complete it from here. I think this works because I tried it one day. There might be other ways to do it, I don't know. Actually that brings me to a question that I was thinking about. Yeah, I mean, is it true that in a polytope, I can write points as a convex combination only in a unique way? That seems too strong in general. I mean, I know I'm not a polytope expert, so if I give you a polytope in any dimensions, I know that every point in the polytope can be written as in a convex combination of some of the extreme points. Need this be unique? Or can it be written as a convex combination of extreme points in two different ways? I don't know. It's not immediately clear to me why the answer should be one or the other. I mean, of course, for a line segment it is clear. If I just take a line segment in 2D, every point on the line segment is actually defined by a unique convex combination of the two extreme points, the two ends of the line segment. But even in a triangle, it seems to be not immediately clear to me why it should be a unique convex combination. It seems intuitively for a triangle in R2 it should be, but I don't see a proof. I've not really tried proving it. Anyways, that's a different point. So the reason I'm asking this is because I know one way to write this as a convex combination of perfect matchings. The question is, are there multiple ways or is there only one way? I don't know. Huh? Multiple ways might be possible?
So, you get a square, diagonals, and then cross take this point. Now this point can be
that's a good point. It's interesting. What Ravindra is saying is, for a square, yeah, definitely, that's right, that makes sense. Well, my square is not a perfect square, but anyways, if it is a perfect square, which does not mean that perfect square, anyways, then this point can be written as half times this point plus half times this point, or it can be written as half times this point plus half times this point. Good, thank you. Yeah. So clearly in the case of simple geometric objects, this statement is false. Now the question is, what about the perfect matching polytope? Can you have the same point be written as two different convex combinations? Anyways, that's besides the point. So now try to see if you can finish this. If you can finish it, let me know. Sure. Okay. You can check out the recording later. Okay, so let's try one more so we got 1/6 times one fellow plus 1/6 times another, 1/6 times n1. Now let's see what's remaining. 1/6 times n1 takes care of these two edges. It doesn't take care of this edge. This edge, 1/6 of it is taken care of, the remaining 1/6 is left. So what I will try to do is I will try to use 1/6 times another perfect matching containing this edge. It's K33, every edge belongs to two perfect matchings. So if I take 1/6 times this orange, I'll take these two edges. Let's try. 1/6 times the orange perfect matching, and I'm going to call it, because I'm using the same edge from the cut. Oh wait, no, the cut edge is actually pink. I should have called it pink actually, sorry. I want this to be pink. And you will see why I'm coloring in a certain way. Okay, I'll take 1/6 times the pink perfect matching, which I'm going to call pink here is M3. I'm going to call it N3. Yeah, I took 1/6 times the pink perfect matching. So that means I'm done with this edge completely. I took 1/6 times yellow plus 1/6 times pink, so I got the whole 1/3 here. Good. This edge is not done yet. 1/6 of it is done. The remaining 2/6 is left, which is equal to 1/3. So let me take 1/3 times another perfect matching pending this edge and see if it works. So maybe now I will use the same color again, but maybe now I'll use orange because I did not use orange in the first one. So now I'll take 1/3 times the orange perfect matching, which will be this perfect matching. Let's try this. 1/3 times the orange perfect matching, which is, I'm going to call it, because it is using the same edge as the pink one here, I will just call it N3 prime. Okay. And now what is left? So this edge is completely left. So let me take it 1/3 times and check what happens. Blue. Let me take 1/3 times a perfect matching in this edge. Which perfect matching? Let me see where I have space. This is orange times 1/3. I don't have space here, so I don't want to take this edge. So maybe I'll take these two edges. No, not these two, sorry. I need to take this edge for sure. And now I'm done, I take this edge. 1/3 times the blue perfect matching. Check if it is correct. 1/3 times the blue perfect matching, let me call it N2. Can you all check if this adds up? Let's see. The edges that are in a single perfect matching, let's just check. Yellow is 1/6, yellow is 1/6, blue is 1/3, blue is 1/3, orange, both of them are 1/3. Yeah, done. Now we need to take care of the edges that are in two perfect matchings. This should be pink plus orange, that is 1/3 plus 1/6, which is equal to half. So that takes care of this. This should be pink plus blue. Pink 1/6. Yeah, thank you. Alright, so welcome back. We had a short technical hiccup. So back to our perfect matchings. These are the 4 perfect matchings we took, and we checked that the given vector is indeed a convex combination of these with these coefficients. Right? Now what we need to do is we need to show that we can write this vector as a convex combination of its perfect matchings. Okay. So there are a few ways to do this. I find the way of Schreiber, which is actually what Amit also did first, to be the simplest in some sense. Although the first time I read Schreiber's, I was confused and I had to actually ask a friend for help. And he was like, yeah, you just do this. I'm like, yeah, of course, yeah, that works. Anyway, so let's see. What we'll do is, we will write everything using the, what is it, LCM? Is it LCM? Lowest common, least common multiple? Okay. Forget the words. Anyways, what I'll do is I'll write everything in terms of 1/6. I can write this as 1/6 times M1, which is fine. I don't need to change anything. This one I can split into 1/6 times M2 plus 1/6 times M2. This one I can write 1/6 times M3 3 times. that is basically this fellow. I can do the same thing here. I can write everything with 1/6. Well, let's do it. 1/6 times n1 is clear, plus 1/6 times n3. This one is 1/3, that is 1/6 plus 1/6, and that is orange. N3 prime and this one is 1/3, that is again 1/6 plus 1/6, so that is N2. Yeah, I wrote everything using 1/6. That makes it very easy to actually combine and go back to the original graph. Let's see how to go from here and here to the original graph. Yeah, maybe you can all try it. DIY. Express the original x as a convex combination of perfect matchings of G using this information. What information? This and this. Oh, I see. I have to. Yeah. All right. So see if you can figure it out. Somewhere you should use the fact. Well, for the example, you probably don't need too much, but you need to use the fact that these two vectors were obtained as a restriction of the original vector. That is actually important. I can't just give you two arbitrary vectors and say that, hey, do this now. We got x1 and x2 by considering restrictions of x to g1 and g2. That is relevant. Okay, if you figured it out, let me know. I'll come and talk to you. Yeah, okay.
The numerator times the copy of the perfect matching containment, that is same on the right side, and you can pair these up and do this for all the edges, of course.
Yeah, so one point I want to mention is we could have written, for example, the left hand side in terms of 1 divided by 12 and the right hand side in terms of 1 divided by 6. But we can also just choose to write everything in terms of the same k, which is what I am doing here, right? Which is what Shriver does. Shriver writes everything in terms of a particular k, which you can always do. Again, taking the LCM on the two sides, right? So, yeah. So if you write everything as 1 by k, then now you have to use the fact that these are restrictions of the original vector. So that actually implies something. So one point I want to make, thanks to Srijit. So this cut C need not be a tight cut. First of all, the graph is not even assumed to be matching covered. But even if you generalize the definition of tight cut, in this example we have chosen C happens to be a tight cut. That is probably the one small downside of this example. And to fix that, what you can do is you can add one more edge here. Then it is not a tight cut anymore. Let me do that. So yeah, if you don't like tight cut, you can add an edge here and put a 0 there. And now everything still works. But yeah, it is good to note that in the convex combination you will write, you will only be using those perfect matchings of G that meet the cut in one edge. The perfect matchings of G that meet the cut in 3 or more edges, you will just take 0 as the coefficient. Those will not be used. Yes. So it is in a sense related to the tightness of the cut with respect to this vector. Right? So let's see if we can. The edge that is easiest here is, I think, the yellow edge. 1/6 times, yeah, 1/6 here. So I'll just take the union of the two yellow perfect matchings. One-sixth times the union of the two perfect matchings, yellow perfect matchings. This is clear, right? We'll take 1/6 times this fellow. Now let's look at maybe this 1/3 fellow. 1/3 is used in the blue one and here also in the blue one. Okay? So we'll take 1/3 times the blue perfect matching. I'll take it twice. 1/6 times the blue plus 1/6 times the blue. That is one way to see this, right? So observe that the yellow simply combines with the yellow because they use a common edge. So I get this plus this and I get that part. Now for the blue, I have 1/6 times M2 plus 1/6 times M2. I have 1/6 times N2 plus 1/6 times N2. So that gives me 1/3 times all the blue edges. And now comes the fun part in this example, where you actually have 3 pink ones and here you have 1 pink and 2 orange. But that's okay because they still have the common edge. The pink one uses this and the pink and orange both use this. That corresponds to this edge. So I'll just take 1/6 times the pink union pink plus 1/6 times pink union orange and 1/6 times pink union orange. Pink union pink, pink union orange, pink union orange, and I'm done. Yeah, you all agree? I'll get exactly this vector, right? So let's do it. 1/6 times pink union pink. So pink will be